Let's look at ways we can store and access information in Android. We're going to talk about the various storage mechanisms that exist in Android, and then we'll talk briefly about the permission system and how it applies to file access in Android applications. Android provides applications the ability to read and write files as you would expect for an application running on a standard desktop operating system. In effect, because Android is built on top of the Linux operating system, underlying the entire framework is in fact the same file system that you would expect on a standard Linux installation. So we have the notion of files and folders, and when an application is installed on an Android device, it is assigned a user, and it's that user that will have permissions assigned to it, allowing it to basically access the file system and other system resources. Android essentially breaks up storage into a few partitions. The first is called internal storage, which is application specific. That is, information stored in internal storage is private to your application. External storage is information that can be accessed by other applications, not just your own. Shared preferences is an abstraction built on top of your application's internal or private storage. And Android also provides a full-fledged relational database via SQLite, and this is available to all applications running on an Android device. Internal storage, as stated, is private to your application. The one caveat here is that applications that share the same user ID, and it's a very technical characteristic, but if an application shares the same user ID, then it can also access an application's private storage. So this could happen if, for example, a single company created multiple applications, specified that they want all of these applications to use the same user ID, and then sign all of those applications with the same certificate, then they would all have access to each other's private storage. Internal storage is always available. That essentially means once your application is running, you can access internal storage without having to verify that it's mounted and accessible to your application. When an application is uninstalled, Android will automatically remove all data stored in internal storage. And when your application wants to access its assigned internal storage location, you would use the filesDir reference or get filesDir if you'd like to invoke a function. And this will return to you a file object representing the base directory where you can begin to store your own files or create subdirectories. External storage, as mentioned, is data that your application can create that is accessible to other applications. Essentially, it's a partition that all applications installed on the device can access. Now, recent versions of Android have placed some constraints on that, and we'll talk about that in a moment. But certainly, if you look at older installations of Android, external storage is essentially shared storage. Dating back to the original context of external storage, which was initially provided by SD cards or external storage cards being inserted into a device, it was at the time possible for external storage to be unavailable. Therefore, you were required to verify that the storage was available before attempting any I/O operation. Today, it may still be the case that external storage is unavailable. However, It's unlikely to be because of the presence or absence of an SD card, and far more likely to be because an Android device can now be mounted to a computer, basically presenting itself as if it is external storage. When that is done, sometimes the device can become unavailable depending on the version of Android and the mechanism it's using to mount its external storage to the attached computer. More recent versions of Android can actually mount itself and still be accessible to your application. Either way, best practice is to verify that storage is available before attempting any I/O operations. It's sort of a little more important that we focus on keeping files in external storage up to date and clean, because when an Android application is uninstalled, not all information stored in external storage will be removed. So if it's information that is private or should not be accessible, well, in that scenario, the information should probably have been kept in internal storage in the first place, but simply be mindful of how and what information you store. When you would like to access external storage, you make a call to the get external filesDir function, where you pass in a string argument representing the type of data that you want to store or access. When dealing with external storage, Android organizes different types of files into various subdirectories. Those are presented here. Examples are documents, downloads, music, pictures, ringtones. If your application needs to store information that takes the key value or name value form, and that data maps to primitive types, so think of integers, doubles, strings, or arrays of those types, then it isn't necessary to write low-level I/O code to store information to files or read that information later on where you marshal and unmarshal the data respectively. Instead, you can simply use Android's shared preferences, which is an abstraction over your application's internal or private storage that allows for basic primitive data that again maps to the name value model to be persisted and retrieved in a relatively straightforward manner. There are a few ways to access shared preferences. A call to get shared preferences from a context object where a file name is passed as an argument will give you a shared preferences object that is accessible and can be used by all context objects in your application. Meaning, if you retrieve a shared preferences object from an activity using get shared preferences, and you provide a file name, store information in that shared preferences object, and then subsequently attempt to retrieve a shared preferences object again from, say, a service or simply another activity. If that shared preferences object is retrieved by making another call to get shared preferences with the same file name, you will receive a copy of the same shared preferences object containing the same information. So that means if the activity stores something, the service would be able to retrieve that same element by simply providing the key. If you make a call to get preferences instead of get shared preferences, you will not be asked for a file name. Instead, get preferences will return a context object specific shared preferences object, that is, one that is tied to the specific activity or service that called the get preferences function. In that scenario, if we were to call get preferences to retrieve a shared preferences object in an activity, save some information with a known key, and then subsequently calling getPreferences on a service and attempting to request the same information by providing the known key, we would not find the data that the activity stored, because those two shared preferences objects would be different because we made a call to get preferences. There is a third way to get a shared preferences object. However, that method ties into Android's preferences system, and that's beyond the scope of this lecture. Once a shared preferences object is retrieved, you have the ability to place information inside or read information from that object. To place information inside a shared preferences object, you first call the edit function on the object. This will return to you a shared preferences editor. Subsequently, you can call a series of put functions on that editor where you provide the key and the value. Once you have made all your put function calls, you can either call apply or commit, where apply will do an asynchronous save, which is the preferred approach, whereas commit will do a blocking save. Your application will pause until the save is completed, at which point commit will return a result indicating success or failure. Apply does not return anything as it's an asynchronous call. To retrieve data from a shared preferences object, you simply invoke get and whatever the primitive type is. You may be asked to provide, in addition to the key, a default value that should be returned if the item referenced by the key is not found. In earlier versions of Android, access to the file system was protected by permissions. Specifically, there were two major permissions: write external storage and read external storage. In the very early versions, despite the name, you needed to provide the read or write permissions to access even your internal storage. That restriction was lessened, and you only needed the permissions for external storage. In more recent versions, these permissions are not required at all. Now, it should be noted that if writing an application or if you encounter legacy code where you find these permissions provided or you need to provide them, the read external storage permission is implicitly included in the write external storage permission. That is, you can either have read permission or you will have read and write permission. You will only ever need to request one permission, and it is not possible to have only write permission. In newer versions of Android, you do not need to explicitly request permissions to access the file system. First, your internal storage is always available to your application without any need for permissions. If you would like to access files anywhere on the storage device, you will need to request Manage External Storage. This is a special permission that can flag your application for review if you attempt to distribute it through known app stores. If your application would like to have file or directory access to certain types of media, this can be done via the newly introduced Storage Access Framework. The Storage Access Framework is essentially a file provider where applications that have information and data that they want to present to client applications can utilize this framework, making it straightforward for clients to access those data. When your application wants to access certain known types of data, such as downloads, It can do this via the storage access framework. This can oftentimes involve the user selecting the data that can be provided to your app, which is why we don't need to ask for permission. If your application wants to access its own data, then it can do that directly without user involvement. Scoped storage is the mechanism that essentially allows this free access for your application to its own data, despite the specific location or type of data that is being stored. So essentially, these two features work in tandem. Scoped storage grants access for your application to its own files. The storage access framework allows you to access files from other applications based on type. The last piece of the puzzle with storage in Android is using databases. Android provides a full relational database system, albeit in a flat file format. SQLite is a database system that is used in Android to provide a full database to each application. You can access and manipulate a SQLite database using your standard SQL commands. However, you can also, and in fact are encouraged, to use the abstraction Room library, which is a part of Android Jetpack. This can make accessing and manipulating and retrieving information from a SQLite database a little easier than trying to access it using low-level operations. Now let's take a look at a simple application that utilizes storage. Here we see an application with a text box where I can type anything. However, if I close this application and I reopen it, my information is lost. If, however, I were to check this box and begin typing again, when my application closes and is reopened, my data is retained and the checkbox state is also retained. Let's look at how this is accomplished by doing a quick walkthrough. First things first, our application layout, of course, has an edit text and a checkbox. Our activity goes through a few steps. First, we have a flag autosave that is set to false. We also have a property for shared preferences that we will initialize in a moment. We have a string representation for a file name, as well as a file object. It should be clear that when we have a file object in an Android application, it is, in effect, a pointer to the file in storage and not the file in memory. The file contents would need to be read from storage. When our application loads, we do a few things. First, in our activities on create, we retrieve the shared preferences object that is specific to this activity because I made a call to get preferences. A call to get shared preferences where I also provide a file name would allow me to get a shared preferences object that another component could access. But since I'm only calling get preferences, no other component can access the shared preferences object that I'm going to retrieve and store here. Next, I'm creating a file using the file constructor that takes a base dir and a file name as a string. This is going to give me a file in my internal storage because I'm using the filesDir reference. This is a pointer to my internal or private storage base directory. So directory name gives me a file. I then query the preferences property, which is my shared preferences object, and I attempt to fetch a Boolean value matching this autosave key. That's simply a unique string that I've defined. If it's found, I will save it here. If it's not found, I'll return false, which will then be saved. The first time my application runs, then this will definitely be false. Depending on the result, I will set my checkbox's checked value to be that result. I then do a quick check. If autosave is true and the file exists, then I want to do a read. So this is just some basic file I/O where I read one line at a time from the file on my storage device, and I place the content in my text box. This could be manipulated to be more efficient, or for different file types, you would do this a little differently. I then apply an unchecked change listener to my checkbox. Basically, I want to know when you have checked or unchecked the box. I first update autosave to whatever the checked status is. And depending on what you've done, I will update the Boolean value that I've saved with a call to put Boolean. I will either save true or false for later retrieval. So this is only to make sure that at the end, when my application reopens, I have the information that I need. To be clear, this information could have been put somewhere else, for example, inside the onStop, where we would only update the shared preferences with the current state of the checkbox once the activity is closing. So we'd have an option there, and arguably that would even be more efficient. What we are doing in onStop, which again is called whenever my activity goes into the background, is I am saving the file. So at this point, I'm just doing standard file output. I take the text that's in the text box, convert it to a byte array, and I simply write it to storage. So this is a standard mechanism to do file output. And I'm only doing that if autosave is enabled when my application or when my activity goes to the background. In my activities on destroy, if I do not have autosave enabled, then the file will be deleted. So all of this together is what gives me the behavior that we observe here. It should be noted that on more recent versions of Android, my onDestroy is not necessarily invoked the moment my activity closes or when I hit the back button. Recent versions of Android simply puts the activity in the background, anticipating that I might likely open it again. So if I was running this on a newer version of Android, I would not notice this behavior necessarily. So it may be the case that I would move this logic into my onStop as well if it was important to me that this file be deleted before my application is destroyed or removed from memory. Alternatively, I could simply do that delete at the time my application starts. If I don't have my autosave enabled, I could simply delete the file. So we could do it proactively or reactively with more or less the same results as far as the user is concerned. So this is a simple example that uses shared preferences. Here we see information being stored. So I retrieve an editor, put the Boolean value, and then apply versus commit. And that is the information that is read at the beginning. I'm using standard file I/O. So storing internal file, reading from that file, and writing to that file. And this is essentially file input output 101, We have other mechanisms we can use. An application that is dealing with other types of media, such as photographs, videos, audio, would do more interesting things. We can tie into the storage access framework and retrieve files, as well as use the storage access framework to present files to other applications that may want them. And of course, scoped storage on more recent versions of Android will govern what type of information we can access. Because of scoped storage, we don't need to explicitly define the standard read and write external storage permissions. So as you can see, I have no such permissions defined here. However, if I was running my application on an older device or I was managing legacy code, I might need to declare that my application uses those permissions here in my manifest. So again, this is File Storage 101.